In this example, we're given a graph and asked to find the intercepts. The intercepts that are being referred to here are the places that the graph, which is in blue, crosses the x-axis or the y-axis. And if we further analyze our graph, we see that that happens here at this point, here at this point, and again at this point. So what we're asked to do over here on the side when we type in this answer is to type each of these intercepts as an ordered pair. It's really important that, especially when you see some guided information behind your answer input, that you're following that very closely. Because if you had only typed in, let's say, the x values, it would kick out the answer as a wrong answer. It wants the full ordered pair. So we want to state this point as the point. It has an x value negative pi/2 and its y value is 0, and you see that here as an ordered pair. And then likewise with the other 2 points. The next part of this problem asks us to decide if this graph is symmetric with respect to the x-axis, the y-axis, or the origin. So what I want to do here is show some examples of different types of symmetry, what those definitions are, and how we can use those definitions to determine the symmetry in this particular graph. So what you see here on this slide are 3 different types of symmetry, their definitions, and an example. So for instance, in this example, this graph is symmetric with respect to the y-axis, and that's because for every xy point, the point opposite of x, y, is also a point on the graph. What that means in terms of the look of the graph is that the y-axis is acting as a mirror. What you see on one side of the mirror is a reflection of what's on the other side of that mirror. Similarly, symmetric with respect to the x-axis works so that the x-axis is the mirror. So whatever you see on one side of the x-axis, like all of this piece of the graph here, is a reflection of what you see on the other side of the x-axis here below. A little bit more technically, what that means is that for every point xy, the point x opposite of y is also the point on the graph. And then last, we have symmetric with respect to the origin. This type of symmetry is more of a rotation symmetry about the origin. For every point xy, the point opposite of x, opposite of y, is also a point on the graph. So now let's look at our graph again one more time and see which type of symmetry best fits. So some of you may look at this graph right away and you see that rotation about the origin and realize that this is symmetric with respect to the origin. If not, I suggest pick an interesting point that is not on the x or y axis and analyze it. So in this case, I'm picking the point pi/4, 1, okay, because I can kind of read that one pretty clearly here on the graph. And if this graph is symmetric about the origin, if you'll think back to our slides earlier, and you can go back to those slides if you need to, you'll recall that the point negative x, negative y, or opposite x, opposite y, should also be a point on this graph. So for this particular problem, what that means is opposite pi/4, negative pi/4, and opposite 1, negative 1, should also be a point on this graph, and sure enough, it is. And I can analyze other interesting points along this graph that, again, are not on the axis, x or y axis itself, and can see that symmetry and how it meets that definition for symmetry with respect to the origin.